Hello YouTube, welcome back to another episode. In today's video we are going to be working on this grass shader that you see here. What's special about this grass shader is it runs without the Unity terrain system and it's completely created on the shader. All of this geometry that you see here is all done on the shader. It's done through something called a geometry shader, so we'll be learning how to use that. And the most special thing about this is it runs on URP, and the thing with the URP is creating shaders with the geometry shader especially is just not possible through things such as shader graph. So you have to use their actual API for URP to get shadows and lighting and all of that fun stuff working. So I've been doing a lot of research into this, so I've got a good idea of how this works. I'm not an expert in shaders by any means, but for those of you who have been following my channel, I'm working on an open world game right now, and as a result of that I've needed a grass system that doesn't work on the Unity terrain system. So I've created this very, I think, beautiful looking shader that can take in many textures, have different varying heights, wind textures. It's basically a very multi-purpose shader. As you can see, it's got a lot of settings and it's just very nice. So like we can go in and tint it. But yeah, we're going to be working on this, and it might be spanning across multiple parts. I'm not sure, but the final project can be found in the description. I've put it in a GitHub repository, so you guys can go pull it without watching the videos. So I hope you guys enjoy this couple of parts of these videos, and I hope it helps you in your own personal projects. So without any further ado, let's get right into it. Okay guys, so just go ahead, open up a new universal render pipeline project in Unity, and you'll be greeted with this beautiful sample project, and we're just gonna delete all of it. So let's delete this example asset stuff. Let's go ahead, delete their tutorial info, their readme. Another thing I wanted to mention about the project that we're creating is a lot of the resources and knowledge that I've gained are through a few very specific tutorials, so I'll be linking those down below in the description. They're not exactly what we're going to be creating today. There's the Roy stand tutorial, which is one of the most major influences that I've had for this project, so I'll be putting that down below. I've made a lot of changes after what I've learned on that tutorial, so this tutorial should still come in handy. So let's go ahead, create a new scene. Let's just call it grass, and let's open it up. Alright, we're greeted with this empty project, and the first thing I want to do is I want to create a plane with a few different subdivisions so that we can get started with having a lot of points on our mesh. So the way that the grass system works is, let me open up my MS Paint. You have your plane here, and we're gonna have it subdivided. So we're gonna have it have a lot of vertices. Excuse my drawing here. And at every point, we're gonna get every point here, and we are basically going to create a plane on the GPU. So we're gonna get each point on the ground mesh, we're gonna extrude upwards and create a plane. So this is gonna be each vertex is gonna be sampled and a plane created from it. Now this tutorial also covers tessellation. So what we will have is we will have this mesh with a couple of subdivisions, but then what our tessellation algorithm can do is basically break up our mesh on the GPU so that we can have much more detailed grass. Obviously this is very performance heavy, so you don't want to use tessellation unless you absolutely need it. So in most cases you should just subdivide your plane, but in a area where you don't want to have like 10 million vertices on your plane, in that case you can use tessellation. So I'm going to be covering exactly how to do that in URP2. So this is going to be a very feature packed episode. So let's begin. So let's first open up Blender and we'll create our subdivided plane. It's very simple. Let's just go into Blender, delete delete. And also, I am not an expert in shaders, so I would recommend having a little bit of shader experience, because I probably can't explain everything from the ground up. It's just the more high level things that I know. So let's go into edit mode using tab. This is new, this is Blender's 2.8, which is absolutely amazing. So let's go and press W, and you can subdivide. Let's subdivide couple of times. That much should be enough. Let's just do it one more time for good luck. Actually no, let's leave it like that. Alright, now we have a subdivided plane. Let's save that. Let's go into where I've saved this, Unity Grass tutorial, assets. Let's create a new models folder and put it in here. Whoops, did not mean to do that. And let's go plane. Alright, another thing that I'm going to be importing, and which you will definitely not have, is the textures that I'll be using for the grass. So that will all be in the description below, so you can go ahead and download that. This is actually the GitHub repository, so I'm just going to go pull it out of here, wherever I've put this. Unity project, yes, here it is. So I'm gonna bring this in, and this is going to contain a bunch of textures, and this actually belongs to an artist. I will be linking his URL down below as well, so you can get this directly from him. So it has a bunch of beautiful grass textures, foliage textures that we can use, and I'll be sure to give him credit in the description too. Another thing is this water distortion map, which will actually be our wave, or like our wind distortion map, and I'll be putting a link from where I got this too. So now that we have these two resources, you should have these resources too by now. If you don't, pause the video, go get them, and we can begin. So now you can create any variations on the grass that you want. So let's go in and bring up this plane and zero it out, and let's just make it 2 by 2 by 2. Oh, here it's a plane. Okay, now the first thing I want to talk about in URP is that you cannot have multiple passes. So in shaders you can have, normally in shaders you can have different passes. You would have a pass for depth, a pass for say tessellation. Wait, you would not pass for depth. You would have a pass for, yeah, usually pass for depth and a pass for the actual geometry. And in the standard render pipeline, you could have multiple of these normal geometry passes, so you could draw multiple pieces of geometry with one material, if that makes sense. But in URP they removed this feature, so in terms of multiple passes you would just use multiple materials here. So you can go ahead and put 2 materials here. So the top material will be the material for actually rendering the ground, and the second material will be the material for actually rendering the grass on top of the ground. So this is how you fake, I would say, multiple passes in URP. So these are the type of workarounds we'll be using in URP. I'm not sure if there's an actual fix for this at the moment, but or if it even needs to be fixed. I think it's not there for a reason. So let's use this workaround for now, and just pretend like this is how it's supposed to be done. So the first material, let's go ahead and actually create this material in our materials folder. Let's create a ground material, and let's set this to a nice green color. We'll change this later. Turn the smoothness down. Okay, now let's duplicate this and let's create our first grass material. Now for the grass material, obviously we'll need shaders, so let's create our shaders folder and let's get right into the actual programming section of this. So let's go ahead and create a shader, and once you create a shader, let's create an unlit shader. Any shader actually should be fine, but let's just create unlit shader and just call this URP grass or something like that. So just go ahead and open up the URP Gross shader, and what you have here is the usual unlit shader. So the unlit shader contains a subshader, one pass, and we're just going to be removing all of this. So this uses the CG program, the usual shader, and this won't work with the URP. If you try to attach this, you'll get a pink material, or maybe since this is unlit it will work, it just won't have lighting, I'm not too sure. But we're going to be using HLSL in this, so we're going to just remove this whole thing. We have no use for it. Now we have a subshader and one pass. So in this episode I've decided that I'm going to work on actually rendering the grass with maybe a material. Next episode I will do depth, so I'll have a depth pass for it, so that screen space shaders and all of the things that use the depth buffer can actually read that the grass exists. And then we'll have maybe another episode dedicated to wind and tessellation. But I'm gonna get the basics down today, or the video will be going on for hours, and it's a lot of work. So the first thing I want to do, however, is get some of the base properties in. So I think the most important would be the height of the grass, to define actually how we want the grass to look. So let's just put in height base. This would be our base height, and this is just how definitions work for properties in Unity's shader system, so that the inspector can pick up on it as well. Another thing I'm going to add is tint, and this would be a color, and we're going to give it something like 0.5, 0.5, 0.51 for alpha. And we also definitely want a texture for our grass, so let's call that the main texture. I believe you can add this tag here, and we're going to call this the base map, and we will call this the albedo, and this will be 2D and white. Alright, so our main base map should take in the grass texture that we want. So if we quickly save this, go back and check out what we've created. Let's go in, and in our grass material, let's just pick this one. So let's call URP grass, and we should have a texture. Oh, I believe we have two main textures. My bad. Let's remove this. We don't want this anymore. Let's put this up here, and let's just call this the grass texture for better naming conventions. And boom, now we have what you can say is the most primitive grass shader stuff that you need. So for the transparency of the grass, if you remember the demo, we're not going to be using actual transparency, we're going to be using alpha clipping. So I'll talk about that later as well. I do have extra techniques to make the edge smoother, but it's not necessary for these couple of videos. That will probably be like part 4 or 5 best case. So once we have these properties in, let's begin creating our first pass. So we'll name this pass, we'll call this the actual geometry pass, or let's, whoops, let me get back onto the screen. Let's call this geometry pass, and we are going to add tags. Now these tags are very important. The light mode equals universal forward. This tells our universal render pipeline that this pass is what's going to be creating geometry. There's other light modes that you can find on the documentation. Another light mode is depth only, and that's the pass that you will need to use in order to write to the depth buffer. Another thing we need to do is up here we need to actually say what render pipeline this is. So let's go ahead and here let's say render pipeline equals universal pipeline. This is what allows Unity to pick up on this shader when we're using URP. So these are some specific things. Obviously you can do these things with the shader graph, but one thing that you cannot do with the shader graph is the geometry shader, and that probably should be supported in future, but I can understand why they don't have it. It's quite a weird one to implement into a node-based system. I can't really see it being implemented anytime soon. But yeah, in this pass we want to add a few which you can call boilerplate code. Firstly, we want the Z-write to be on. I don't know if it's on by default. We want the code to be off, so meaning since we're drawing planes, we want both sides of the plane to be rendered, so we want that on as well. Okay, now let's create the HLSL program and end HLSL. Now this is where all the code is going to run. This code is in HLSL, like I said. The reason it's in HLSL is because Unity's URP libraries are all written in HLSL. So if we want to get lighting data, if you want to get fog, all of that, it's all done in HLSL. I'll show you exactly, actually. Let's go into our let me get into the Grass Shader tutorial. And if we go into our library, package cache, and universal render pipeline, shader library, this is probably the most important set of files, as well as shaders. All of this is very important to understand how the URP library works. So if I open up core, you will see a bunch of useful stuff like get camera position, world space. All of this stuff is absolutely important for you to write shaders in URP. So first thing is first, we're going to actually include some of the files that we're going to be using. So these are the include files that we need. And I have linked my GitHub repository down below, so you can go copy these files in. If you don't want to type this out, or else you can pause the video. And I'm also going to paste in a bunch of boilerplate code, so forgive me for this wall of text that I'm going to put in, but none of this actually has any significance except for the last couple of lines. These allow us to use the light maps because our grass responds to baked light maps, and also fog. We wanted to be able to respond to fog. And the thing that I learned about fog, you guys might already know this, I found it interesting, is that fog is actually done on a per vertex basis. I always imagined that fog in Unity was done on a screen space basis. I thought it was always a post-processing effect, but turns out fog, when you go into the lighting settings and turn it on, it's actually done per vertex. So this is why we need this pragma here. And yeah, so once we have this stuff, I'll explain what this does. So this pragma required geometry is extremely important. It tells our shader that we're going to be using the geometry pass, which usually no one does, and these tell us what the name of our functions are going to be for each pass. Now the way the different passes work, let me explain this to you. First is the vertex pass. It loops through every single vertex, and we can assign vertex data or get vertex data. Then the second one, so you can loop through the vertices in the vertex pass. That's first. The order is very important, and once it loops through, you can say, for example, move up or down these vertices, it doesn't matter. Second is the geometry pass. So once it goes from you can pass in the vertex data into the geometry shader, and then you can add extra geometry. So that's second. And then third is the fragment shader pass. That's where you actually write to the screen. So that order is quite important. So let's just keep that in mind, and we've called this a lit pass geom, lit pass vertex, and lit pass fragment. So if you want a second to copy this all in, you can. It's not really that valuable for me to go through what each of these do, and I honestly don't know either, so let's just leave it at that. Now one thing I'm not going to do is write the actual shader code in here. I don't think it's worth it for me to write the actual shader code in this file. This is going to be more of a master shader file, and because we're going to use multiple passes, that's going to have to re-render the geometry the exact same way. For example, the depth pass, right? It's a separate pass. We need to run this exact code that we would usually put here in there, and wouldn't make sense to copy paste everything that we write here into another pass. So we're going to actually include another file. So we're going to include the grasspass.hlsl. We haven't created this, of course, but we are going to. Now we're going to save this, and the compiler is going to yell at us because it can't find any of these things because we haven't created it yet. So let's go ahead and do that. We can't create HLSL files directly in here, but we can open up Notepad and let's just save as. I just open up Notepad, save it as, and let's create a grasspass.hlsl and all files, and I'm just going to save it in the same area as urpgrass where I've got this. Let's press save, and it should show up with the HLSL file, and now this is where we are going to put our code. So this is a HLSL file, and let's begin actually coding it. So what we want first is two structs. The struct that is going to be gotten from the GPU, giving us vertex information, and the structs that we're going to pass into the geometry shader and the fragment shader. So I've already constructed these, so I'm going to copy these in, and I actually got most of this from another GitHub repository that explained how to create custom URP shaders. So this is all from there. I've just changed quite a bit regards to what we actually need for this tutorial, and I've omitted stuff that doesn't make sense to have. So I'm just going to go through this. So the attributes, this is a naming convention for what we require from the GPU to define our vertex data. So let's go ahead and actually create this. This is the vertex pass. So we're going to call this varyings. Lit pass vertex is what we called it in our master shader. Attributes input. Now remember, these definitions that we've given here is telling the GPU what our functions are called, and now the GPU will see that we're requiring something, an input that's of type attributes. So go over here and look at our struct and see, okay, this guy wants the vertex information of the object space position of the vertex, the OS's object space, the object space normal, tangent object space, the UV of the current vertex, the UV of the light map of the current vertex, and the vertex color. Now, vertex color does not mean the visual color that you see. The vertex color is like a separate way of encoding information into a mesh to do other things. So if I go quickly into Blender here, and we created our plane before, actually, if I open that, we'll actually do this later, but what you can do is if I go into the, I believe, vertex paint, I can paint colors onto this mesh that aren't actually visible. These are colors that I can use to encode new information. Now what I was using the color for in the shader is I was saying, well, wherever there is green, wherever there is a green vertex, add a geometry for grass there. So for what we can do is I can paint it like this, and we can check the vertex colors. Note that this is in vertex paint. We can check that the vertex color is green, and if it is, we only add grass there. So we can create a path here with no grass. So that's what vertex colors are very useful for. So that's why we're bringing in vertex colors. Instance ID, I believe this is for GPU instancing, which we are not doing because it doesn't make sense for us to instance. If you want to instance this material, if you're using multiple different planes with multiple different grass shaders, please go ahead and instance this. I believe you wrap all the properties in some instancing thing. I'm not too sure about how that works exactly, but you might have to do some research into that. I don't think it's that difficult. So once we get this information from the attributes, we have this varyings. Now this is all the information that we are going to generate from this attributes, and we're going to generate this information. As you can see, this is the return type of the vertex, and we're going to send this to the geometry shader so I can use that, and that is going to send another version of varyings to the fragment shader so that it can draw it on the screen. So these structs are automatic. This struct is automatically filled in. this struct we will have to fill in ourselves from information that we generate. Okay, hopefully that was useful. What we're gonna do first is we're gonna use Alt Shift. I'm just gonna bring in these in here and turn these into floats. So float, and this will just allow us to access the properties. So let me actually just create a place for this so this doesn't get messy. Okay, oops, that's just my phone. Okay, now we also want to get the main texture, and I believe we can get that quite easily, but we'll worry about that later. So let's create the actual vertex pass now. So what we want to do is we want to create an empty varyings, and we'll call this output. And yeah, that should just be it, just an output, and we're going to be filling in this varying using the attributes information so we can pass it over to the geometry shader. First thing, output.color. As you can see, we have the vertex color. We just want to preserve this from the input.color because we're not going to be changing this. We just want to pass it along until the geometry shader. Okay, we're just passing this along. Next, it would be to get the position in world space, I believe, because this position is in world space, this position is in object space. Another thing, yeah, these are all in world space, and what actually is written to the screen, like the screen space position, so you have object space, then world space, and then screen space, which is like, I believe 0, 1, it's just like 0 to 1, 0 to 1 on the y-axis, and it's what you're drawing on the screen. So that is what position CS is, screen space. So we need to write to that as well. We don't actually need to mess with that at the moment, I believe, because we don't have that. So all of this is simplified using URP's libraries that we have imported. If you remember back here, we imported this, and they have a bunch of useful stuff to convert everything basically. So we're going to define this. It's called vertex position inputs, and you can find this, I believe, in the core library or something like that, and we can call this vertex input, and get vertex position inputs is the function, and we pass in the input dot, I believe, position OS, and once you pass in the object space, it automatically generates the world space and screen space of the position. Now, the thing that I haven't addressed is position, world space, and fog factor. So XYZ of this is the position world space, and the W at the very end is the fog factor, so how much this is affected by the fog, and there's a function that does that already for us. So we have the vertex input, and we have the exact same thing except for normals as well. So we're going to call this vertex normal inputs. And now these functions, like I said, you might want to look through the core library, because that's where all of these gems are. So vertex normal input, get vertex normal inputs, input normal OS, input tangent OS. Now we're passing the normal and tangent. Just a quick reminder of what normal and tangent are. If you have a plane, your normal goes straight up perpendicular to the plane, and the tangent goes parallel to it. And we have another one, I think it's called the bitangent, and that is the cross product of these two. So it will either be going in this direction or this direction, and these three create what is called tangent space. And now tangent space is very important, especially for our graphs, because we want to make sure that no matter what orientation of the plane we have, that the grass is always pointed in the outward direction. So we will be doing something called change of basis matrix multiplication, where you can get the object normal, multiply it by the change of basis. No, sorry, we can get the tangent vector, multiply it by this change of basis matrix, and then we can get it in the object space normal. So that's stuff that we'll tackle in a second, but first let's fill up the vertex shaders to continue that. Now we want to compute the fog factor like I was talking about before, and there's a handy function that's called compute fog factor. Vertex input dot position cs dot z. Alright, just don't worry about this right now. Basically we're passing in the z coordinate of the screen space in order to compute the fog factor, and the fog factor is connected to the lighting settings that you have in Unity. So all of this like the color and all that, not the color but how much fog is controlled back in Unity somewhere. They're doing it, some voodoo magic back there. Next thing we want to do is we want to get the UV. We want to set the UVs of the vertex. So let's go transform text. Now this is a very handy function. So I will pass in our base map, which is not actually called our base map. Our base map is called, oh, it is called our base map. That should be fine. A second. Alright, so the transform text function, basically what it does is it allows us to I believe it maps it changes the base map depending on its tiling and offset factor. Those two change here. So if I go back in here and open up the material, these are all new things to me that I've been learning, but basically the tiling and offset, these two things, in order for that to affect the texture, you need to use the transform text, and we're basically mapping it onto the inputs UVs. So I believe that's what is happening here. Please correct me if I am wrong, but yeah, we need to use transform text in order for that to like the offset and tiling to work correctly. Next thing is the output dot UVLM, and that is just literally just gotten actually no, this is some weird equation. I'm actually not sure how this works. I'm gonna be completely honest. I believe I got this from the same GitHub repository I was talking about in regards to their custom implementation for the URP pipeline. So don't ask me how this works because I'm honestly not too sure. But this is the light map coordinates so that the baked lighting data can correctly be added to this. So just copy that down, and if you want to do further research into that or explain how that actually works or what it's doing, please tell me. Yeah, I believe this, actually no, I'm not even going to try to explain it because I'm not actually too sure. But the next thing we want to do is we want to set the position WS and fog factor, and we want to create a float for vertex input dot position world space and our fog factor. So the vertex input dot position world space is generated when we code this function here. So the world space is automatically created from the object space, and then the fog factor we just calculated here. So the world space has x, y, and z, and then the fog factor takes up the w, and this is a float 4, not a float. Next is normals. We want to say output.normal ws is equal to vertex normal input dot normal ws. Next is the tangent ws, vertex normal input dot tangent ws, and you see how all this is very easy because of URP's libraries. We literally just coded a bunch of functions, and now they gave us the normal tangent. We didn't have to do any of those calculations that you would have to do usually on the standard pipeline. Now The bitangent, I believe, is used when we have a normal map. So you can see here we have a define here. If there is a normal map, then only will we have bitangent in the varyings. So we're gonna fill this up if there is a normal map. So you don't need to worry too much about this. Just put this in. If a normal map is defined, then just add this, set it up. Basically, we're just taking it again from the vertex normal input. Now, next thing, this is another if condition. If the main light produces shadows, I believe is what this one is, and if we want to set the shadow coordinates, and we're going to use another helper function, get shadow coord and vertex input, and that goes back to our position. So if I believe if the main light has dynamic shadows, then we want to get the shadow texture from the GPU and get the shadow coordinate of this current vertex, and the shadow coordinate tells us like whether how much of this object is in, I think whether this vertex is in shadow or something like that. I think we sample the shadow texture later on, but we'll get more into that once we actually reach that point. Actually, also up here, we want to set output dot position cs equal to vertex input dot position cs output dot position os, because we need the object space as well, because we're going to be using that in the geometry shader. Ideally, I think in retrospect, I think I should have split this up into what I want to pass into the geometry shader and what I want to pass into the actual fragment shader, but that's fine. You guys can do that if you want more optimization, but this works perfectly fine. It's just a bit long for setup. Position OS, and we're going to, at the very end, finally return output, and all of this gives us a grand total of nothing. All this has done is gotten the vertex data and created a varying struct from it, and we're going to send that to our geometry shader, and only then do we do. Okay, so I've come to a realization that the geometry shader is massive, and that's just the start of it. The fragment shader itself has its own behemoth of work, including lighting, translucency. So this is how I'm going to break it up. We've completed the vertex shader, and the tutorial's already reaching around 30 minutes. So I'm going to finish it off here today. All we're going to do is I'm going to define the geometry shader, explain that, define the fragment shader, explain that, and then I will cut it off. And in the next part, which I'm going to release extremely soon, maybe in the next couple of days, I will have a detailed explanation of how that works. But don't worry, I am providing the full source code, so you guys can look through it, and once I release the tutorial, you can understand what's actually going on, or most of you will just pick it up anyway. So let's create the second definition, is the void lit pass geom. Now notice that this doesn't actually return any values. Instead, it brings in values, and it uses the in-out keyword of shaders to send out data. So these may be some completely new data types that you have not seen before. This is the triangle data type, and each index 0, 1, 2 would be the different points, and each point would be of type varyings. And we'll say this will be our input, and we want 3 because this is a triangle. And we can access input 0, input 1, input 2, and we can get the different varying positions. And remember, this is our vertices being passed in, except they're being passed in based on the triangles. So now we can average the position of these 3, and we can get the center point of each triangle. So this is extremely powerful. Now what's even cooler now, what we can do is we can say in out. Now we can either pass out a point stream, and we can pass out a bunch of points, we can pass out a bunch of lines, or we can pass out a bunch of triangles. Obviously we're going to be passing out triangles, so let's call this triangle stream varyings. Remember, we're taking in the varyings and then we're just passing out varyings, and we're going to call this outstream. Now, there's one more thing we need to do for a geometry shader. It's called the max vertex count. So let's call this here max vertex count. And what we want to do here is know how many vertices we need. So let's actually define this. What we need here is one triangle here, and this is 1, 2, 3. And we have the other triangle, which would be 4, 5, 6. So all we need here are 6 vertices. So let's set the max vertex count to 6, because this is how much we're going to be sending out. Now we have the geometry shader set up. Now what I was thinking is that I could just for demonstration's sake for this episode, to finish it off by you having something visual, we can pass out a point stream. And as a point stream, what we can return is we can just return the different triangles. this is how this would work. I would go outstream dot append. I would append input 0, outstream dot append input 1. So append is just we're adding to the stream here. Outstream dot append input 2. Now we need to separate each one of these. We need to tell our GPU that these are different points. Now for a triangle stream, we would do this differently. For a point stream, however, we say outstream dot restart strip. I believe there's a restart strip. Maybe there isn't. I'm actually not sure. But we would do this for a point stream. Now, what you would expect actually is a bunch of points wherever the vertices are. If this works, it works. If it doesn't, it doesn't. I'm not too sure. But obviously, the next thing, once we have the geometry shader, is the fragment shader. So basically what I've done here, just to be clear, is this is not the grass shader. This is just a bunch of points that I'm rendering at each of the vertices for you to see the power of the geometry shader, basically. So lit pass fragment is the name of our fragment shader. So we're bringing in varyings as our input, and now normally you would stop here and say, all right, cool, let me start using these inputs to create the fragment data. But what we want is kind of different. We also want one additional piece of data, and I did not know this existed. This is so cool. You can say bool vf sv is front face, and sv target, that just means it's rendering to the SV target, I think. But SV is front face. This boolean tells us whether or not we are looking at the grass from the correct normal direction. Remember, we have culling off, right? So both directions we can view the grass. So the problem occurs with that when you have lighting and you want to say, okay, like, how darken this area and like make sure that the dot product, because the way that lighting, dynamic lighting is calculated is using the direction of the light and the direction of your normal and calculating the intensity of the light that hits the surface. And the problem when you have culling is you don't know which side the normal is, because you define the normals to go outwards in the surface. So you say, okay, here's the normals, and you say, well, in the geometry shader you would define these triangles and you'd say, well, I want the normal to go in this direction, but it culls in both directions, and this is a two-dimensional object because it's a plane. So how do you know whether or not you are looking at it from the correct direction and what normal direction it should be in? Because it's a two-dimensional object, but you can see it from both sides. So this is what this boolean allows you to do. It tells you whether or not you're viewing it from the front face, and if you are, then you can keep the normals how they are. If they aren't, then you can reverse the normals in the fragment shader and make sure that the lighting is accurately calculated. This is important for all planes, especially billboards, all of that stuff. It's important to know this, and I was really excited when I saw this, because this was actually a problem that I was tackling without knowing this was a thing, and it almost seemed impossible. And I saw this and I'm like, oh, okay, so this is how you do it. It's almost kind of like a cheat. There's no like real way I could have known, but yeah, now we're just gonna return I don't know, like 1111, and that would just be white, I think. So we're creating points and we're returning white. This might work, it might not. If it doesn't, I'm just gonna leave it there, and we'll change this to triangle stream and begin the actual video in the next episode. But according to what I've seen, this should all technically be working. Oh, it does look like it's working. Now let's go into our shaded, and you can see that we've left two open materials here for the different shaders, for the different passes, our virtual passes, our fake passes, you could say. Now let's drag a grass material on here, and boom, you can see now that the geometry shader has drawn a bunch of points. If I go into wireframe, you won't be able to see it because it's on there, but if I change this, if I remove the ground material, or change this to 1, you will notice that there are just a bunch of points. Now that is your geometry shader. Now let me show you one more thing that you can do, just to demonstrate how restart strip works, because it's quite an important concept. If I change this to line stream, I would actually be creating this line. I would define this as a line and I would restart it, and I would say, okay, I only want lines to be created between the first and second vertex of every triangle. And there you go, you get this beautiful pattern here, and so you can see that the possibilities with the geometry shader are absolutely endless. And this was created without even modifying the positions. And our final one would obviously be our triangle stream, which is what we are going to be using. You would pass in all three, 2, and you would have your normal mesh. So there you go, that's how we would begin it. I'm going to just leave it like that because we are going to be using the triangle stream. Add the second material again, add the ground material, so that we can begin with this next time. One thing to note is that the console will continuously yell at us. Actually no, here it will tell us that it has more materials than submeshes, and this warning should not be ignored. It's basically saying that this is not an efficient way to do it, but they actually haven't given us another way to do it. So this tells us that this is probably, like, we probably shouldn't be doing this, because this is rendering this mesh twice, and it is, like, it does affect performance. So if you had a lot of these meshes, it would be important to look into a different solution, because you wouldn't want 1,000 different planes being rendered twice, because it's just unnecessary. Then you would have to start looking into render passes or something like that. I'm not really sure if there's an alternative, but it's definitely important. And if Unity, if you're watching this, please leave a comment down below telling me how you guys can fix this. But yeah, this is how to begin developing grass in Unity. I hope you guys have enjoyed, and hopefully we can have some Legend of Zelda type grass by the end. Yeah, thanks for tuning in, guys. I hope you enjoyed, and I'll see you next time.